Right, okay, so we've collected our information and we've put them into the computer. Okay, so there we go. Right, so what we've got is we've got the first bowl and we've got the second bowl and a table of information that's been derived from the original data. Okay, so what you have is the gains in poundage in the first column, which is then converted into inch pounds of energy, which is divided by 12 into foot pounds of energy. But the problem with the foot pounds of energy is it's a little bit overinflated. Okay, the way the steps work on the graph. And the most simple way of trying to work it out is by taking the last column of information you've got for the sum, so it's the addition of the first inch, second inch, third inch, and then at the fourth inch, for example, you would add in half of that value, or it would be a full value until you went to the fifth inch, and then it would be half of the fifth inch. Okay, so what you do is you'd add up all of your data all the way down to 28, then you would not add the full value of 28, you'd only add half the value of 28. Now that's the most simple way of trying to describe how to get a much more accurate value for stored energy. Okay, just add half the value. Okay, so now the stored energy per pound of draw force is very much like what they talk about with electric cars and petrol, diesel, right? The energy density that you have in diesel and petrol far outweighs anything you'll get in an electric battery, right? So that's the density, that's the amount of energy you can get per kilogram of whatever it is. So a battery simply doesn't store the same amount of energy as the petrol equivalent. Now, if you were to look at the stored energy per pound of draw force, the same as you would for population divided by area, you'd end up with the population density, which is the number of people in that area. You could then look at energy per pound held. So that's the stored energy density of the design at each inch of pull, and they're not all equal all the way through the ranks. Okay, now what you'll find is that as soon as the graph starts to go upwards, and I'm jumping ahead of myself a bit here, is that the energy density starts to drop as you hit stack. Okay, so there is the draw force curve. Now what we've got here is two bows at quite an extreme end of the range, right? You've got very, very conventional, so I'm getting buzzed by a fly. You've got very, very conventional in the blue with the preload bulge, and then it starts to dip as it goes up, and then you've got a much bigger, much more elongated super recurve gain. Okay, so there's what you've basically got, and that goes out to 28 inches for a medium limb. Now the blue line was on a 27-inch riser, the orange line was on a 25-inch riser. They were both medium limbs, but they were both fully out, and they were both at roughly the manufacturer's bracing height range. So that isn't a bad estimation as to what you would get. Yeah? Now, what you're looking for is the area under the graph, which is what the stored energy tries to calculate. And the stored energy is the area under the graph, and of course the orange line has all this extra energy. And it takes energy to throw an arrow, so the more energy you've got, the faster you can throw the arrow. Okay? So here you can see that the preload etc. of the two bows, the higher preload of the super recurve gives you the higher stored energy, but then as the bow gets mega smooth, the energy starts to take off. Now what you'll notice is that when you start running out of limb length, then it starts to flatten off at the end. Okay, but anyway, the stored energy of the conventional recurve obviously isn't quite matching up, no matter what part of the draw length that you're looking at. Yeah, So that's the stored energy of the two different bows. Now you can see, if there's only 1 pound in draw weight difference, there's actually a considerable amount more stored energy in the design, especially when the smoothness kicks in. There is absolutely no logic in the world as to say why a bow that stacks would be faster. Okay, so let's not go there, right? Now your self-perception, your idea as to what you like in the draw, that's totally down to you, but there is absolutely no logic. Would stand any rigour against some serious questioning with regards to why you would like stack in a bow. Okay, now I did drop my paper, but here we go, the last bit. This is a smoothness graph. It's a bit wobbly, right? And what we've got here is the energy of the two bows. You'll see the smoothness on each inch as you go through. So what you're looking for is a good initial start, and as you go down, one maintains the 2 pounds per inch gain, whereas the other one dips nicely down to the smoothest part of the draw and then starts to climb back up. Okay, so if you've got any questions about any of that, how to achieve that, how to get there, just give us a shout, stick your questions in the comments below, and I'll do my best to answer. Alright, thanks for watching.